of HPC, but it's something that you guys are using whether you even realize it or not. And we're looking forward to presenting this and then hearing what feedback, or maybe even, if you have things to add that work for you. Maybe we'll have some time at the end for that. In any case, we're going to talk about build and runtime environments, or just more generally speaking, a cluster environment or a multi-user environment. And we'll talk about exactly what that means in this context. But the goal today is really kind of conceptualize and demonstrate some of the concepts. Talk about when we say certain words, what exactly those mean, how you can kind of map what we're talking about to actual hands-on practical tools and methods. And specifically in the context of a cluster environment. And cluster is a multi-user environment. We see from all the time, people that things work great on their laptop. They have full administrative control, but maybe they have very specific and less dynamic environments, which we'll talk again about. But when you move into a cluster, the fact that you kind of lose that a lot of that administrative privilege, and you're working with a lot more of a dynamic software inventory where things can quickly get out of sync or out of compatibility. The concepts and things we'll talk about today deal with those types of issues. How can you work around not having that administrative access and keep things nice and clean and encapsulated, and make sure that you have an efficient environment that works to build and run software? Okay, we'll talk about concepts. We'll talk about environment modules and environment variables. Really, they're a lot of the similarities. I mean, modules are really just collections of environment variables and other configuration settings. But we'll talk about some tools and methods for dealing with those. We'll talk about common paths and files to look out for when you're building software and using platforms like R or Python. We'll go through a demonstration, which should be interesting because, as I mentioned at the beginning of the, before everybody had kind of gotten into the meeting, some of it hastily prepared, but sometimes those live without a net demos are fun. But bear with me as I go through the demo, try to get my thoughts together. And hopefully by the end, we've got a tool that's, we've developed and tested, had a couple of iterations, but we've assisted a couple of researchers with some automation, which is it's a script that sort of automates these steps for setting up an R. It's really a setting up and a methods for setting up R build and runtime environments and keeping things consistent. And so we'll provide you guys with potential tools that might be useful for that. So everybody's kind of familiar with this. Feel free to ask questions during the presentation, but if you do, just put them in the chat or raise your hand. If we have time at the end, we'll open up the mics, but I think everybody's got that figured out. All right, so let's go through quickly some environment concepts and terminology. All right, an environment. Well, an environment, that's the kind of a broad term. And in the context of HPC or computers, an environment or software, an environment is similar to, the environment that we find ourselves in as humans, right? It's there are certain things we have to adapt to. There's certain things that can constrain what we can do in the environment. And it's similar for software. A software environment is really sort of a collection of properties or settings that influence the operation of the software. And that influence could mean not just, a functional piece of software, an operational piece of software, but, a broken one as well. And what you find yourself doing in cluster environments quite frequently is trying to manipulate the environment as best you can with the permissions that you have to accommodate what a particular software package or library needs or expects. And so when we're talking about environment throughout this presentation, we're talking about a software environment or a computing environment, and we're pretty much talking about a collection of settings that can be modified or manipulated to make things work. All right, so the term build is interesting because not only is it overloaded, it's sort of recursive. And it can be used as a verb or a noun, really. But in the verb sense, when we say, hey, we're going to build a piece of software, that's really, we mean we're going to take steps, perform tasks on the command line to translate source code into machine code. And so, and an example of the use there is, hey, can you build this Python instance for me? Or can you build this SAMtools software for me? And as a noun, you could say, hey, we've got a build available. We have a build ready. We have provided a build. That's in the noun sense. And so that's really, as I mentioned, kind of recursive. it's the result of a software build. A build is the result of a software build, and its use might be something like, hey, Matt, that Python build that you got out there is really borked or something like that. You know, that's how you would refer to it as a build. Or Matt might tell me the same thing. And then, of course, runtime. So those are the three things you saw in the title of the presentation today: build and runtime environments. Runtime is essentially, you know, that sort of same idea of a collection of properties, but it's the properties specifically for executable software and the execution environment or execution context in which it's running. And so inside that runtime, you have some other types of terms. In terms of the build environment, you've got the term compile or compiler, and that's a tool that helps turn source code into machine code. And a compiler, in a lot of cases, it sort of takes the first step at getting that source code into a form that can be processed by the hardware. But part of that process, near the end of the build, you'll see something called a linker, or it'll link certain things. And when you're just talking about linking, you're talking about bringing in dependencies or external software or libraries and combining that together with this machine code that's generated in the compile process. And so linking is really important, especially with what we do, because what we do is point to a lot of different locations on the system that are, very core libraries that provide core functionality to the software. And so the linker makes sure that all of that is pathed correctly and that the software knows how to get to all of these dependencies that it needs. And then you have a tool chain. So that's just really a set of compilers, libraries, tools, utilities that all work together to complete this process. And so when you hear of things like the GCC tool chain or a CMake tool chain or the Intel tool chain, it's really just a collection of tools that assist with the build process. All right, and so now we'll get into more of the runtime type terminology. And this is runtime terminology that's really specific to, I guess it's mostly specific to interpreted languages. Now, interpreted languages, while we've just talked about, building software using compilers, is really a way to try to ease the burden of the compiling process, of the build process. And the way that works is, just like you see in Python or R, when you write your Python or R code, you don't normally have to go through and do any kind of, GCC this or that. You do R script or R or Python and then the name of your Python file, and it just runs that. But in the background, it is doing, I guess you could say it's kind of a flavor of what they call just-in-time compiling, but it's translating that source code sort of on the fly, closer to runtime. I think it does it actually sort of, it does a lot of pre-processing before actual runtime, but it's very much closer to. You don't have the steps and tasks that you normally take for compiled software. And so when we talk about a platform, we're talking about a collection, much like the toolkit, a collection of tools, libraries, and then this term middleware that enable, a specific language to function on a system. And that one core piece to that functionality is the interpreter, which again translates that source code sort of on the fly at runtime. And then a very important concept for people who use things like Python, R, Conda, is this virtual environment method. And that is critical for that use case on a cluster, because it allows you to really manipulate the environment to sort of encapsulate settings that will, change paths and give you more control and customization over how you want to use that platform. Specifically for package installation. If you try to install packages just by, like you would on your normal workstation without any changes, go and say, hey, pip install whatever Python package. Normally that's going to work just fine. If you try to do that on Easily, it's probably not going to work unless we've got the permission setting correctly. It shouldn't work. And so how can you get around that constraint? And a virtual environment, it's not just that, it's more to it, but very important to know that that capability is available on many platforms, and learning how to use that is a real benefit to your workflow. All right, so let's just kind of try to conceptualize how that all fits together. You got your build, your runtime, you got your build, and then you got this middleware term, and then the operating system. And each of those layers, starting at the bottom with the operating system, kind of influences the layer above it. and without the layer below it, each layer is pretty much inoperable. So without the operating system, you can't have middleware, and without some middleware, a lot of times it's not necessarily the case, not a hard constraint, but most things use some sort of middleware in the background in order to function. And that just sort of sits between. Oh, sorry. That middleware sits between.
Thank you.
Okay, sorry.
Got somebody. Let me get that. If somebody could get the mic, there we go. Thank you. Sits between your software and the operating system, and it handles things, like a device interface. How can you take it, communicate over the network, or how can you use a GPU? And so those are more, you have less control over that middleware, but it serves a really important purpose. And then as you move up, you go into the build sort of layer, and that's where you're, again, turning that source code into machine code. That's where your compilers live, your compiler-related environment variables, which we'll talk further about, and then on into runtime. That's after you've built the software or after you've configured your platform environment interpreters and set things the way that it expects. Then you're into runtime, and that's really just more in the context of a running program, software that's in its execution or that is executable or potentially executable. Now, just because you have an interpreted language that doesn't use a compiler, I guarantee you there is a compiler involved somewhere in that process. That Python binary or the libraries that are in your Python or R platform were built with a compiler. And so what we see quite commonly is that people will, attempt to use a Python or R or language platform module and run into issues because the underlying compiler or build environment is not quite in sync, or maybe it's incompatible with what was expected by the runtime. And so that influence, as you move up those layers, everything is dependent upon its previous layer. And so it's important to make sure you get things right, starting from the bottom up. Hopefully that kind of gets your, a mental, or excuse me, a visual representation that makes sense to you. The only thing that's a little bit weird is this middleware piece. As I was thinking about it, I was thinking it really more in terms of the lower level. Things like MPI, which uses a middleware piece to really communicate with the InfiniBand fabric, or a GPU device driver. Those device drivers are installed on the host, and they're really kind of embedded into it. You don't have a lot of control over a device driver that you can make during while the system is running. But there are some middleware pieces in between build and runtime, and I have an interpreter here set at the build level. And quite honestly, I think, there's probably an additional layer that belongs in between the two there. But just to keep it simple, those four layers are really the ones maybe conceptually to remember. All right, so let's talk about environment modules and environment variables. We've kind of established some terminology and maybe got a little bit of an idea of how to conceptualize what's going on. But we have these things called environment variables, and essentially environment variables are the main thing that you can use to prepare your build environment or runtime environment to support software. And some common ones that you'll see, especially when building software, are this CC or CPP or CXX environment variables, which set compiler paths. You have this path environment variable, and I'll demonstrate the use of that and show you kind of the importance of environment variables and how powerful they can be. But by manipulating that path environment variable, you can put things in your execution path so that you don't have to, / run it or give it the full path. It just sort of recognizes that, hey, this path has binaries in it that I can execute. The LD library path is a linker sort of thing. And it says, hey, look in these locations on the file system. And this is usually a set of directories, a collection of directories, more than one usually, that says, hey, I have libraries in this file system location or these different directories in the file system. You have the C flags, which are really your includes. So a lot of times software will use something called header files or library headers, include files, and that C flags environment variable tells the compiler, or maybe the interpreter, where to look for include paths. And so if you have a bunch of header files somewhere in your home directory, you can manipulate that, and your build should pick it up and say, okay, I'm going to look in these locations. Similarly with LD flags, those are library paths that are specific to, in addition to the LD library path, that are much more specific to the build time environment. And so how can you kind of see exactly what's going on with your current environment? You've got one already just by virtue of logging into easily or logging into a Linux system. There are certain environment variables that are set by default, and you can view those. If you know the name of it, you can say echo $name, and that $name is, when you see that $sign and then it's followed by text. Now, when you see this $sign, and I know this is confused, I probably should use a different character for the prompt, but this is the prompt. Following that, when you say echo $ in this name, that's the name of the environment variable. This is the value, really. This is the value of the variable. But if you don't know the name, you can see everything that's set currently as an environment variable in your shell session with the env command, env. And then you can optionally use the grep search utility, string search utility, to grep it for specific names or patterns. And so that'll allow you to display your current environment. And then if you wanted to modify it, you can use this export command. So when you do this inside a session, you run export, that globally sets the environment variable so that it is at a very high level in your session, and it's not something that you're just using specifically for one task or process. It applies to all the processes in the session, and you can export it with this generalized syntax. Export the name of the environment variable without the $sign. Okay, so that's how Bash or most shells work. When you're setting a variable, you use a name equals, and then following that, you can set whatever value you need to set. In most cases, it's a string, and I would argue in most cases, it's a path to a file system location. But you can not only just set them specifically to a single value, but you can also prepend or append values to existing values in an environment variable. So in this case, we're appending right here, this first export path, we're appending home username custom bin to the existing values in path. And it's a colon separated list in this case. And I think environment variables really, the vast majority use this colon to delimit multiple values. The second example, here we are actually prepending a value to the existing LD library path variable. So you can do it without these, you can do it with them. When you're dealing with environment variables that have been set by the system, it's highly advisable to append rather than just replace them wholesale. So that's how you display and set or modify environment variables. But it's much more convenient to use module files, environment modules. And if you were to look under the hood in an environment module file, so I'm not sure, but I think probably most of you have used the module command to load a specific software module if you've used the cluster before. So you may be familiar with a lot of these, but they're very important for what we're talking about today. So some basic commands you may already be familiar with. You can search what modules are currently available with module avail. You can give it an optional query string, which will filter it out for a pattern that you're searching for, or a word or software name. And then once you find software that you're looking for, you can use module load, and module load loads the module into your current environment, and that essentially modifies your environment to use the software as we've defined it in a module file, as the admins have defined it in a module file. We do our best to make sure we include all of the potential settings that are needed. In some cases, we have to iterate them a few times, but vast majority of the software that's been in existence on the cluster has got the environment set properly. And then module list will show you what current modules we have loaded. And so that's important to check every so often to make sure that you got the right compiler, the right version of R or Python loaded. And then in the more advanced use, as mentioned, you can look under the hood of a module file. And when you do, you'll see there's a lot of this business going on. Export. It's different syntax because module files use either TCL or Lua. But essentially, you're doing the same thing. You're prepending or appending to environment variables, and there are some other things that may not be quite. There are different methods, not necessarily setting environment variables, but maybe loading additional modules or steps that we think are necessary to use the software. But if you run module show, it'll show you exactly what's happening under the hood when you're loading a module. Module reset is something that you can use if you get things a little bit out of control. Maybe you've loaded the wrong module, your builds just aren't acting right, and you just want to reset and kind of let's start over. All right, we take it back down to the defaults. Load a compiler, then load the dependent module, so on and so forth. Module Spider is more of a full search, and we'll talk about module hierarchies, compiler dependent modules, but that'll allow you to search the full module path, and that's an environment variable. As you can see, all capital letters with a $sign that tells the system where to look for module files. And so this module spider command will do a more thorough search than module avail. You can actually search module files with regex, which that's a more advanced use. Most people may not find it useful. For R users, though, that's handy. You can, if you search for do a module avail R, it's just going to search generally for the character R anywhere in the software name. But you can use regex if you're like an R user to search for, okay, everything that begins with a capital R, show me that. And that'll give you just the R modules. And then we run this quite frequently as well. LMod, the underlying module file platform, it maintains a cache in your home directory. And when we install new modules, or maybe if you're creating your own modules, there's a way to do that with the module use statement. I didn't include it here. Sometimes they don't show up. It's like, well, I know that module file's there. And so you can use this ignore cache, which will show you, hey, keeping the cache out of the loop, here's what I see. And that is a good way to check for new modules that have been installed if they're not showing up. All right, so we'll talk about module hierarchies. And when you do a module avail, you'll see at the end of it on easily, there's a note there at the top. And modules and dependencies may change when loading or switching compilers or libraries. Check the compiler dependent modules section in module avail. Additional modules available with the following. And then there should be some compilers shown there. But if you think about that, what it's telling you is, hey, if you load a compiler module or maybe a core library, you might see a change to your module path. There might be some additional modules available when you do that aren't normally available by default. And so when you do a module load GCC 840, for example, you'll see this second box here, where these compiler specific groups of software libraries, languages, and things like that. And so that's good to know. Now there's not only debate, I think, internally with the sysadmin about when is the right time to use these compiler dependent modules, because it does introduce it's just not convenient to say, the comment I hear quite frequently is, when I do module avail, just show me everything. Why is it hiding these module files? And it's really just a kind of, it's the nature of the way it works, but it does, by doing that, it kind of constrains what you're allowed to load. And by constraining what modules are allowed to load, in the case of a compiler specific module, one that was built with a very specific compiler toolchain or build environment, it really kind of forces you to think about what you're doing. It forces you to think about, okay, if I'm going to load GCC 840, I need to make sure that I've got the right dependent modules loaded. And so there are benefits and disadvantages to using module hierarchies, but we implement module files both ways. And so that makes it even kind of more uncertain. But as I demonstrate these things, maybe it'll become more clear. But module hierarchy is important to note, especially with what we're talking about today. In the case of R, which is very picky about the underlying build environment and has lots of nuances with the way it does its build environment settings. So yeah, module hierarchies to ensure the compatibility between build and runtime environments, minimize module fragmentation. You don't want to have to load libraries that were built with 6 different compilers, so on and so forth. And more importantly, in the context of research, we've already gotten enough uncertainty to deal with. We're doing research, trying to do experimental things where we're not sure what the result's going to be. We're trying to find out. And if we can just avoid any additional uncertainty, that's great. And so it kind of, module hierarchies and maintaining that relationship between the build and runtime environment is just an efficient, sort of minimalist way to do things, and it reduces a lot of the potential complexity or uncertainty. Okay, so some useful commands here that we use quite frequently when troubleshooting. Someone comes to us and says, all right, I've tried to install this Python module and I'm getting these error messages. First thing we want to look at is the environment. And so what we might say is, what is the output of which GCC? That'll tell us where is the, in your current environment, where does it think the GCC compiler is located? And that'll tell us, hey, if it's in, user SBin, that's the system compiler. Or if it's in tools GCC 840, that's one we installed, that's GCC 840. The echo statement, as mentioned, shown earlier, how you can display an environment variable, the env command, and then you see where we're piping it into this sort of strange looking syntax with grep. And we have that / pipe that's separating these words. And what that does is give you, it's an OR. So you can grep for, Python or GCC, or so on and so forth, any kind of pattern you could put there. LDD, very important. So if you run LDD on a library.so file, and that's a shared object file, you'll see them in error messages quite frequently when things are missing, or on a binary, an executable, something that's been compiled. It'll show you where it thinks its dependencies live. And what you can see when there's a problem is that the output from LDD will show a missing link to a library.so. And then it gives you a clue to say, oh, it's the zlib compression library. It can't find that SO. Maybe I need to load a zlib module. So that gives you really good clues to what's going on as to whether or not you set your environment correctly. And then, of course, the export command, which we've already talked about. All right, so we've talked about environment modules, environment variables. Let's talk a little bit about configuration files. And these language platforms I mentioned, like Python and R, quite frequently use very specialized configuration files, though there are a few that are pretty ubiquitous that you'll see in your home directory already. They're created when your account's created, and they're sort of system or shell level configuration files that might be influencing your environment. And so if you haven't already, take a look in your home directory. And when I say $home here, that's actually an environment variable as well. Now I use a little bit different syntax here. I'm using these squirrely brackets, and that's just, it does the same thing essentially as back here where I didn't use the squirrely brackets. It's the same thing. It's just a different type of syntax that Bash uses. And so you'll see me mix that up every so often, so apologies for that. But it's the same thing. This is an environment variable that says the location of your home directory. And inside your home directory, you have a bash RC file and a bash profile file. That's assuming you're using bash and haven't removed the default profiles. That's bash is the default shell uneasily. But these get executed every time you start a new shell session. So when you log into the cluster, or even when you submit jobs, unless you explicitly tell Slurm or something to ignore these are getting loaded. And we see this quite frequently, especially with conda, which if you run a conda init is nice enough to go in the background without telling you and modify your bash RC file. So now every time you log into the cluster, it's doing some kind of conda operation that's setting a path that you may or may not want. And so take a look in there, make sure that it looks nice and clean, and I can show you what the default looks like. But those bash RC and bash, this dot character in front of a file or directory is hidden. And so you have to run a special ls command to see them, but these are there. There's also one for the module files, is .lmod, and then this one is used quite frequently. It's sort of a standard location where various software will store data or configuration files. So it might be worth a look to look in home.config. Those are the shell or system configuration files that might be of interest. Now, in terms of the platform files for Python, you have things like home.python or home.conda, and I think .conda is actually a subdirectory, not a file, but there are potentially files underneath these. But those are of interest when you're using Python. And then when you for R, which we'll talk about today, I think there's one additional one here, and just ignore this. Whenever you see the pound, that's a comment. I guess I didn't complete my thought here, but these three R configuration files are probably in your home directory if you've used R. They may or may not be, but if they are, you want to keep an eye on them because they do set certain environment settings, runtime and build environment type settings that influence your R behavior. All right, so we're going to move into the demo here, and just give me a moment to get staged up. I'm going to pause my share. But while I'm doing this, I'll ask the admins to maybe field any questions that might be in the chat, or we'll open up the mics just for a couple minutes while I'm getting staged up, and people can just kind of ask them verbally if they prefer.
Yeah, this is Jeff. I'm gonna, just while it's going, I'm, nouns, verbs, as it relates to HPC, and all this other goodness of environment. It's really a get what you want kind of meeting. It's just fantastic so far, Bradley.
Thanks, Jeff. I'm glad to hear it because, as mentioned, I found myself hastily preparing, so I'm trying to do my best to articulate these things in a way that makes sense. If I'm not clear and somebody knows a better way to state it, or if they have something to add, by all means, jump in there. But just give me a couple minutes. Thank you, Jeff. I appreciate that.
Yeah, and just beautifully presented. I love the graphics there. I mean, I'm in my mind though, I'm thinking we need to do something like an HPC Mystery Theater 3000 where it shows us in the viewing room and we are making comments when we rewatch it. But that's probably for another day. But it's really great stuff. Great stuff. And it might not hit you until next week, but this is gold.
Hey, Jeff, speaking of watching it, Chris put a link out to our YouTube channel, AuburnHPC. So if you didn't get that, that's a good link, and we'll upload this recording there, sometime this afternoon.
Yeah, that's great. That site, we probably have some more in the can that we can put in there. I know Bradley has been somewhat of a one-man pre and post production shop. He's done some great job on touching these videos, preparing them, doing a little light editing. But it's good stuff. Good stuff. Yeah, and Cassie, I mean, I see Cassie was out there asking questions about that. And, take this back to your colleges and, spread the word on this, because there is so much goodness in this from just getting started on this, because, I'm sure you're probably aware, any of you that support things where you get a lot of the same questions from different people, and things like this that really teach you how to go about troubleshooting things. There's a lot of people that need to see these videos, and obviously a lot of you are the researchers and not so much the facilitators in your area. But if you are the facilitators in your area, or you collaborate with other people in your area, point them to this, because there's a lot of good stuff in here. So yeah, I see Bradley, I see that you're up at the prompt.
Good deal. That's what I was going to ask if you can see my screen. And I've already talked for 40 minutes. So let's get on to the fun stuff here. All right. So let's take some of those things we've just talked about and maybe see what they actually look like when we get our hands on. So first, I'm just going to do a module list. So I'm already, I'm logged into the cluster here. And actually, you know what? I'm going to, those bash RC files. Let's take a look and see what happened when I logged into the cluster. So this, if you're not familiar, let me get that a little bit larger for you, maybe. This tilde is a shortcut to your home directory. You can do it like this, or you can do it like you saw on the slide there, home.bash rc. Different ways to do things in Linux, always a different way to do something. You can see I've got a bunch of stuff in this bash rc, but a lot of it's got these pound signs in front of it, and that means it's commented out. So you can see that I made the mistake of running a conda init at one point. It put that in there for me. The reason I don't like that is because it's setting a specific path that I may or may not want to use. I might have multiple virtual environments for Conda, and I don't want this to load every time. So I've commented that out. I've commented out some of this other stuff. But you can see there are, and these are in the default bash RC, which gets copied to your home directory when your account's created. So it loads a default version of a GCC compiler, and it loads the slurm module, and that exposes the commands like sbatch, salloc, things like that. Without the slurm module, you don't even see those commands. And so you could venture a guess. Remember that path environment variable that we talked about? I'll bet you if you look at this slurm module file, you'll see it's setting a path that points to where those sbatch and salloc binaries live, or executables. I think this is also a default thing saying, hey, if this file exists, then source it. Again, it's sort of strange. Oh, that's the Etsy bash. So that's one that lives in a system path. And it's saying if that exists, go ahead and include that as well. And so the system administrators, if we found something we thought would be useful for everybody in the cluster, something we needed to do to apply to everybody's shell session, we might put it in this etc bash RC, and then that gets included as well when you load this. So you can see how that can sprawl out of control. But that's what you might see in your bash RC file. You can modify it because it's in your home directory to do whatever you prefer, whatever you like. Just be careful because, as mentioned, it gets executed with every shell session, every job, and you may not be aware. You might make a change and forget about it. I do it all the time. Realize why are things acting so funny? It's because I did something in my bash RC. But we saw those module load statements in the bash RC, and let's just see if those actually worked. And sure enough, modulo GCC modulo slurm loaded this one, loaded this one. Now, if we were to look at that module file, let's do a module show. Module show slurm. Okay, and as I suspected, you can see it's not using that export command, but it's using a similar one. And I bet you under the hood it's doing something, probably an export command. But it's prep-ending, and it's prep-ending our path with this CM shared app slurm current bin. And if we were looking there, we'll probably see sbatch, salloc, things like that we run. But when you prep end the path, this is important to know, bash is going to look for things left to right. And so what appears first, in other words, if I had another slurm path somewhere in here, bash is going to pick the sbatch or salloc command that appears first, left to right. So we got some prep ends, and these are all prep ends. We're not doing any appends here, and we're really, not doing a whole lot. The man path is an environment variable. It's just like man pages. So this is your help, your documentation. Here are where some libraries live, and Slurm may need to be aware of where those are. So you set your LD library path. And then in some cases, we actually set both LD library path and library path. Some software just disregards this, and so they like this better. So sometimes just to make sure we got it, we'll do both. And then we've got a C path, which is sort of like a C flags, another derivative of C flags to show where the header files live and things like that. So that's an example of what Slurm did, and you can see. Let's just do an end statement. All right. Now when I run this, remember this command is going to show me all of the environment variables that are currently set globally in my session, and I'll bet you it's going to be quite noisy. Let's go ahead and see. Yeah, it's a big mess. All sorts of weird stuff set in here. You've got these like color codes, here more paths to things, so on and so forth. So what can we do to clean that up a little bit? Well, let's try that grep statement, and let's see if we grep for slurm or something like that. Slurm. Well, didn't find anything. Well, let's try grep-i slurm maybe. That's a case insensitive search. And now I found some stuff. So we didn't find an environment variable that was named slurm, but we found some occurrences of the slurm keyword in our environment. I wonder if there's anything in here for like GCC maybe. Yeah, okay. Module path's got some GCC references in it, but really not a whole lot to speak of. So here's an important one. CC, now currently set to user bin GCC. That's the system compiler. And if we were to run a which GCC, that's another command we mentioned, that shows us, we didn't even have to use the m command. It shows us where it thinks GCC lives. Now, when I haven't loaded any additional modules, I'm going to see where does it think R lives. And it tells me there is no command R in anywhere in these locations. And these locations are the same locations here. So you can see it's looking in the path to see if there's R. It's not in there. All right, well, we have some R modules, and let's do this regular expression thing just to show the R modules. And so I did module dash R before the command, and then gave it this $R. Now this is a regular expression operator that says the string begins with, and there's one called $, which is ends with, but this is a way to just show me the R modules without a lot of noise. Now, you can see it's got R languages under a compiler specific category. And what compiler do we have again? We had GCC what? Well, it's here. Let's try this. Is there a -- version? Sure is. Okay, so it says it's 485. And if we do a module list, That should match, and it does. So this would indicate that these versions of R were built specifically with the GCC 485 toolchain in mind. These are ones that were built with, well, we're not really sure what. So what can we do if we wanted to use one of these to maybe, if we wanted to try to maintain some compatibility, what can we do? Well, let's just do a module show on these. This is a non-compiler dependent one of the standard install. And it's setting these things here. So we know where the paths are, and this bin or this lib64 folder might be good places to look to see if we can get any clues as to what compiler was used. And let's do an ls on those. Okay, let's see what's in here and what's in lib. So the bin for binary and lib for library folders are usually of interest because those are going to this is going to contain executables usually or binaries, sometimes not. But this is almost always going to have some kind of shared object or .so library file living underneath it. And those .so files, again, you'll see them in build processes. Those are what your linker references when you're building, and that like third-party dependencies or libraries, so on and so forth. So let's look in there. Let's look in the lib folder. There's our SO files. And let's take a look at that one. And then let's do an LDD. Remember that LDD command? That's a linker command or a linker utility that'll show you kind of information about what was linked. And when we run that, look at here. We got some problems right off the bat. These are not found. So if our software attempts to instantiate any of the functionality in these libraries, we're probably going to get a runtime error. We may or may not. If it doesn't attempt to use it, it might work. But it shows us a lot of things live. And a lot of this is pointing to places in user lib64, so on and so forth. And so let's see. What if we were to do a command? Let's do a command called strings. Okay. Strings tries to extract human readable strings from a machine, machine code type binary. And it's a so if I run that without any greps, it's just going to give me a bunch of garbage. But if I do maybe grep-i GCC, interesting. It's coming up with a lot of 9.3.0. Now it does have a reference to 485. And, that's kind of a head scratcher, what was going on there. But I think a lot of these will have a reference to 485 because it's the system compiler. But I'm thinking because we see 9.3.0 is so prevalently here, if we really wanted to try to keep things nice and consistent, we might load the GCC 9.3.0 compiler. Because it looks to me like this version of R was built with that. Now, if we already know, maybe we have a compiler, a preferred compiler version, or we're going to use R and we're going to use some additional software, and the minimum requirements for our R packages that we want to install or our additional software say, hey, we need a compiler that's over this version. Maybe it needs something over version 7 something. So what can we do? Let's do a module AV GCC. Now, GCC is not the only compiler, but it's the most commonly used one. And we can see that we got a few different versions of compilers. Now, you don't have compiler-dependent compilers, really. Those are sort of atomic. But currently we have this one loaded. And maybe our requirements need something higher than 7. So we're going to do a module load GCC 8.4.0. All right. And then you can see that the module command has told us, hey, we have replaced this compiler, GCC 485 with GCC 8.4.0. LMOD attempts to constrain you to one compiler at a time. It doesn't like loading multiple compilers for pretty obvious reasons. And so it has an underpinning that says, hey, if we see a compiler, something we think is a compiler being loaded, we're actually going to have to take any existing compilers and get those out of the way to load it. So now if I do a module list, you should see we just have GCC 8.4.0. And now if we do a module avail again, or module AV for short, we'll see this time at the top, and that's because the ones that appear at the top will override any naming conflicts at the bottom. For example, we have a compiler specific R432 But then we also have an R432 down here. And so we want to make sure that if we load a compiler specifically, that the versions of R, these compiler dependent versions get loaded by default and don't get squashed by the more general ones. So we've loaded this GCC 840, and now we know these languages, these compiler specific languages are available. So let's go ahead and load this one. R432, and let's just show that module as well. And you can see we try to put some notes about how we built it, what our module files look like at build time, right? And this is what was loaded when this was built. So you may want to match that if things aren't working correctly, or you use your LDD command and it says, hey, I can't find this, Java SO. You might say, well, let me look at the module file, see what was loaded during build time, and you can replicate that. But down here, with these compiler dependent modules, the pathing pattern we try to use, it's mostly consistent, but has to be changed in some cases. As you can see, it points to the software name, the name of the compiler version, and then the software version. And then, of course, for any of these specific header paths, library paths, so on and so forth. So that's the way we kind of self-document on a compiler dependent module, what compiler version it's, and we can install multiple versions. You might have a 432 that's for GCC 5.3 or something or other, but it keeps them separate and encapsulated that way. All right, so now we've got our GCC loaded and our new R loaded. And so we've got a good, we're pretty certain that because we've done that, we've maintained the compatibility and the expectations between our build and runtime environments. The GCC 840 being sort of our core build environment, and then our R432 being our sort of core runtime environment. But as I mentioned, there are some specific configuration files that languages like R and Python use. And let's take a look at some of those. If I ls my home directory for .r, I don't have anything, it doesn't look like. And so that doesn't seem right. Profile. Oh, man, that's because I'm in /r stuff. And we'll do maybe D. So there we go. So I've got this ALD. This is for show me the directory. Don't go into the directory and recursively list the files. But you can see we've got this one we can ignore. That's different. But we have this R subdirectory, this R environment file, this R history, and then this R lives directory. So we've got all sorts of stuff that's tagged with R. And if we were to look in some of these, we might find that it's pointing to specific places. And here's now are some R specific environment variables. R lives user, R lives site. If you look at the R documentation, there are all sorts of environment variables that might influence your build. And I've seen where sometimes setting this works and these don't, or sometimes setting this works and this doesn't. And so what we've done is kind of try to keep things consistent and assign it to all the ones we're aware of that point to R lives. And in the documentation, I believe you'll find this is where it wants to install packages. So let's take a look inside there. All right, so this is actually a symlink, but it points to this folder. So let's look in there. And here we see a bunch of subdirectories, and these are R packages, R modules. They've been installed here in my home directory. Now, if I didn't do anything to create an R virtual environment, this is done with an R virtual environment, you wouldn't see these things. You probably wouldn't even see a lot of these R artifacts in your home directory. It's probably going to use the one that's the default system globally installed configuration. And to illustrate that, maybe we let's see, what would be a good way to illustrate that? It may not even be necessary. I guess maybe it's a good opportunity to explain virtual environments and demonstrate why that's such a big deal. All right, without setting these language specific environment variables and having these different files in place, and I want to go and install an R module, it's going to use the default configuration. It's going to try to install an R module somewhere in /tools R whatever, and you're not going to have permission to do that. And so for those that don't know, they're like, hey, I need to be able to install modules. I don't have to go and do a software request for every single Python or R module I need. And this allows you that control. And so let's see what time we got here. I think I slated this for 11:30, so we got a little time. And I don't want to get ahead of myself, but I am excited to get into sort of the automation part of it. And also it helps me remember maybe some of the constructs I'm missing. So we've talked about an R virtual environment and setting a path to where you can install packages. Let's take a look in our R profile, if we have one. All right, in R profile, I don't see a lot about environment variables in here. We see this this is R syntax, and it's setting certain things. And I think what we are dealing with here is when R, the interactive R shell loads, it will read this R profile by default, if it exists, and it execute these lines. And so when we go into R, we can see, it's giving me a nice welcome message here. I'm gonna welcome it, and it was set by AUHPC automation on this date. And so we run some kind of utility that's put this in our R profile, but you can put whatever you want in your R profile, similar things if you prefer, and do handy stuff like, by default, there's no package repository set. So R will come up and say, hey, what package repo do you want to use? Well, here we're setting it to use something so we don't have to be asked about it. We don't have to set it. It does this every time we launch R. Here we're blanking out our library paths. I think this is probably a bug or something that I did in testing. But let's just look at lib paths. This is an R command. There are similar commands in Python and languages that show you where it thinks it can install packages. And currently, as I mentioned, this is a system or a path to which we don't have write access, presumably, because it's in our globally installed R package. So let's take an opportunity to say, say, what was that path that was in our libs? Where was it? Here it is. Let's go ahead and do this. Let's say, modify our profile manually. And I'm going to go ahead and just put that in here. And let's see what happens when we do that. Now, it may be that we have to remove our R data file, but let's see if it worked. Oh, it's .libpath, sorry. I'm not an R, I'm not the greatest at R. All right, so now, previously we had only this, but by modifying our libs runtime, I guess, variable, more than likely it's doing something under the hood that's doing an environment variable manipulation. But this libpaths function takes whatever we give it and puts it in our library path. And so now, if I were to do a, install package is BIOC manager, for example, it's probably going to tell me it already exists. It's just the one I can remember. I guess it's going to say that doesn't exist. My manager. And it says that one doesn't exist, but it gives me a suggestion. Maybe you meant this. Nice and case sensitive for us. So let's make sure we're getting the case right. And you can see it says installing into this directory. So that lets us give us a control over that. Now, when it does this package install, okay, may not be all that apparent, but in the background, R is going through and saying, okay, I need to install a package. I'm going to go and get the source code for that package, and I'm going to sort of try to assist with the build process for that package. So it is in the background using a compiler and a compiler, suite or set of tools, a tool chain to perform those build steps. And what we see a lot with R is if you don't have your build environment set correctly and you go to do these package installs, it will fail. And it's not very clear. A lot of times it keeps so many things in the background, it obfuscates so many of the details. And there are ways to tell it to do traces and things like that, debug. I can't ever remember the syntax. But it'll complain a lot about a lot of things if something is just not quite right. And then you have to go and dig into it and see, oh, what's happening here. This package throws this error, go out to Google and search for it, so on and so forth. But if we make sure to keep our build version, GCC, whatever, Intel compiler version, whatever, toolchain, whatever version, and our R or Python or runtime platform, the compiler suite that was used to build it, if we keep those consistent, we can avoid a lot of those things. All right. So that's a demonstration there of both the environment variables, which we saw with that R libs, which pointed to a location, as well as a way to do it in your R profile using an R command. Now, for build and runtime environment, this is really important. If you have one of these, and this is a subdirectory, and in that subdirectory there's a file called makevars. If you have that file, make sure that it's not interfering with your build stuff. If you go to install an R package that's throwing errors, this is one of the first things you want to look at. This is an R specific type thing, but it has, as we mentioned, these sort of build specific environment variables. So this R makevars file is a build time configuration file. The R environ file is recommended use is to set environment variables in there. And that's what we're doing. And then, of course, we have R profile, which is much more of a, use R commands to do similar things or anything specific to when you launch your interactive shell. So those three things covered there. Now, there's also one more important component. I don't know if I have the file, but we have seen this cause problems in the past. And there is an R data file sometimes. All right. And if that exists and you switch your version of R, switch something about your build or runtime environment, this retains, in some cases, artifacts from the previous R version or build version, and it can cause problems. So it's best when you're creating a new virtual environment, or really every so often with some frequency, go through and clear this R data file. You can back it up just like any normal file if you wanted to keep it for whatever reason. But that's also an important one to know that wasn't included in the slide. But we've seen that cause major problems, and it took a long time to figure out it was that. So one tidbit of information that might really be of use to you. So we've talked a little bit about how R sort of instantiates these concepts and uses build and runtime environment variables and how to load the modules and things. But what do we do when we want to actually put it to use? We want to create a new, let's say when you use a new version of R, and we want to make sure that we're keeping things all nice and tidy, it's keeping it separate from any maybe existing virtual environments. And there are methods to do that. But I think R, the vast majority really, and there, when you use Python or Conda, there are commands you run that will actually go ahead and perform the steps to create a virtual environment. R itself, while it refers to virtual environments, really just advises you to set these environment variables in certain ways to enable that functionality. So let's look. We've got a script, tools, scripts, AUHPC, R, I believe. So we have a script here, AUHPC runtime, that we've had some success with that performs a lot of this grunt work for you. It looks in your home directory, checks for the existence of certain things, backs them up for you, and then creates you saw those symlinks that were used. And right here. So these are symlinks. This is a file that points to another file. And this script, what it does is it actually performs, writes to these locations, but it's then symlinks to it. So then it's easy to say, okay, I can have a bunch of different R profiles in various locations, but then all I have to do to activate a specific R runtime, R build and runtime, is change the symlink location. And so that keeps everything. You don't have to change file names. You don't have to delete or move things. You just get rid of this symlink and point to something different. So you can see these should match. These are currently pointing to 930, and I've got 840 if I'm not mistaken. So let's give it a shot with that script. So again, tools, scripts, AUHPC, R, AUHPC-runtime.sh, I believe is the one we want. And it says, oh, you'll have to source the file. Okay, so some scripts are designed not to be run directly, but to be sourced. And the reason we source a script instead of running it directly in our case is because when we're setting environment variables, if you're to have a script, execute a script that sets environment variables, once the script is done and it's finished running, all that goes out the door. It just kind of it runs in a sub shell and then it goes away. But by using source, we can actually manipulate the current sessions environment. So we're going to do that. We'll take its advice and we'll say, all right, instead of running it directly, we'll source it. You can do that with either source or that dot. I'm going to use the explicit version. All right, so it comes up and it says, oh, okay, you know, hey, give me a warning about log files. Don't worry about that. But it says, hey, currently you have an 840 GCC 840 compiler, and here's where the executable lives. Here's the version number it sees, and you also have this R platform version 3.2, and here's where the executable lives, so on and so forth. Do you want to use these? You know, and yeah, sure. Now the way it figured that out, it looked at our currently loaded modules, and so when you run this script, it's best, although we have some logic in place, if it doesn't find a compiler and or a R version loaded. It should have come up and prompt you and ask you what compiler, what R do you want to use. I'm not sure if that's been fully tested. So in the meantime, go ahead and load your compiler version and load your R version first before sourcing this script. And then let's see what it tells us here. All right. So it goes through and says, I'm going to validate your environment. It checks for the existence of these known influential files and warns us about it. And it's going to say, all right, you know what? I'm going to back those up. I probably should put something here. Where did it back it up to? I don't even know where it backed up, but it says it backed it up. So we'll take its word for it. And once it kind of goes through and says, all right, these files are currently, let's get those out of the way. Then it's going to go through and tell you, all right, here's what I'm going to do in terms of where things are going to go. Here's where I'm going to install the various components, various files for this combination of build and runtime. The build environment stuff's going to go in that .r folder. The runtime stuff's going to go here. R build settings, so on and so forth. It's just telling us where it's putting things. And you know what? I don't have any objection to that, even though the paths are quite long and cryptic looking. But we are going to see what happened there. Where? All right. So module extension like the so something happened on this module load. That's a bug. I'll take a look at that. But it happily continued, and it said, all right, I did this with the .r. Okay. Here, it failed on this R lives directory. The reason this checking is seeing, does this exist? It said no, and so then it created it for us. So that failure is really just a warning, and if it's followed by an okay, we're good. So it created these R environment paths. Then it copied our reference runtime configuration file, which lives, I believe it told us where that is. Runtime figure. I think it's this base file. It's copying that to the location. And those base files really just contain what we think is a good baseline, very bare bones configuration for R. It can then be modified based on your preference. But this should set up a really clean, minimal R environment that now has the path set correctly to use that combination of compiler and runtime. And let's just check ourselves on that. It says it's activated by enabling this. What does this now point to? Previously, it pointed to like a 9.30 version, I think, didn't it? Well, now it's saying, no, that's 840. So what was our LSAL-R star LD? All right. Our R profile now points to a GCC 840. What about our make vars file? Make vars now points to GCC 840. Okay, great. And what does this R environment file look like now? All right, well, those are pointing to symlinks, so let's just double check those. And good, we're 840. So we got all our stuff in place, these known files that influence our build environment. And so now let's just, let's just check. Let's run R and see what happens. All right, well, you can see this message is now different. It gives us a different date. I think it's the same version. we can be pretty sure it modified our profile okay. And did it set our lib paths correctly? That's key. And fortunately, it did. So if we were looking at our profile, it probably got it. So now it's done all this grunt work for us, and we're all set. We've got a nice, clean GCC 840 R432 environment in which to install packages. So let's give that a shot. All right, says it's going to install here because it's unspecified. And let's just see if this build works. And when we get this message done, everything looks good. And so from this point, we can install whatever packages we want. It's going to keep it all nice and tidy in this specific pathing, naming convention. It's going to create symlinks where needed so that we can quickly switch from one environment to another, so on and so forth. And if you're an R user, we recommend please give that script a try. And if you have suggestions, modifications, or problems, let us know. But that kind of wraps up. While I didn't go in depth maybe as much as I wanted to on some of these things, I feel like it's a good place to kind of wrap up our discussion. I think we've met our goal of demonstrating the concepts and then doing some hands-on practical work with it. Ultimately, to show you a automation tool and the power of using these scripting type methods to keep environments consistent, keep paths consistent, and you can even add more to this in your workflow. If you're doing experiments that, you're running stuff all the time, it's dropping, your output files are all mixed up together in the same directory, so on and so forth. You can use scripting to tag things with dates or tag things with versions and maintain a consistent directory structure so that you always know, okay, the output files that live here with that experiment I ran with these specific versions, so on and so forth. Improves your reproducibility, lessens the burden of all the staging and pre-processing that you do, and just makes things a lot more clear, reduces that uncertainty and complexity. So I'm going to wrap it up, stop talking, and let some other people talk, hopefully. And I'll just sit back and listen.